All right, so for our introduction to bonding, this is how we start our lesson, and that is, are we able to pick out the difference between ionic bonds, covalent bonds, or substances that have both just by looking at the formula and understanding where the metals and the nonmetals are differentiated on the periodic table, which is that stair step. So you have the metals all over here, up here above the stairs we have the nonmetal, and we're talking about, you know, boron, aluminum, silicon, germanium. So that stair step going across the periodic table over there. So again, up here are the nonmetals. So above the stairs, below the stairs, down here are the metals. And what we call an ionic substance, I mean, the real definition is you have a positive and a negative ion. But we have a metal positive ion bonded to a nonmetal negative ion, or polyatomic ions. So positive, negative, polyatomic ions. What we call a covalent bond would be two or more nonmetals. So two or more nonmetals, a metal and a nonmetal, or a polyatomic ion associated in there. So then which ones are both? So let me just start at the top here in CO2. So both carbon and oxygen are both nonmetals, meaning they're both above the stairs, and so that makes this a covalent bond. So what we're going to do is we're going to get a little more in depth as to what that means. All right, this one has the positive and negative polyatomic ion ammonium bonded to the negative chlorine. And so this would be an ionic bond, but polyatomic ions themselves are two or more nonmetals bonded together. And so they're held together with a covalent bond, whereas the polyatomic ion and the negative chlorine are an ionic bond. And so that's actually both. Nonmetal, nonmetal, covalent bond. Metal, nonmetal, ionic bond. Polyatomic ion. So that's held together with covalent bonds, and then the positive 3, negative 2. So this is both ionic and covalent. Covalent, two nonmetals. Covalent, two nonmetals. Covalent. Ionic, metal, nonmetal. Covalent, covalent, nonmetal, nonmetal. Polyatomic ion, covalent, but plus 2, minus 2, ionic. So once again, that's both. And this would be an ionic bond. You have a metal bonded to a nonmetal, positive 2, negative 2. All right, so that's how we could pick it out. And, you know, that seems like a complicated question at first, but you can see it's actually pretty simple. All right, so jumping right into bonding, we are going to talk a bit about bonds, molecular shape based on those bonds. So what shape does the molecule assume, and then polarity based on that shape. And it all stems from this idea of electrons, because really it's electrons that are moving, doing our bonding. And let's say, for example, we have water. You know, water is an oxygen bonded to two hydrogens, and you perhaps have seen a structure like that, where you have one oxygen in the center, the hydrogen's coming off of that oxygen. But do you really understand what's happening? Well, this is a covalent bond. We would predict it to be covalent because we have H2O, nonmetal. Remember, hydrogen, though it's way over there in the first column, is a nonmetal, bonded to oxygen, which is a nonmetal. So you have two nonmetals in the bond, so it's covalent. Which means, if you perhaps have learned this before in your science life, that you're sharing electrons. But we're going to see that that's not a great definition of a covalent bond. All right, so what we've learned about the atom is this right here would represent oxygen, and it has this electron cloud. Well, floating around in the electron cloud are those electrons, obviously, and of which oxygen, if it's a neutral atom, you know, it has 8 protons, so it has 8 electrons. So there's floating in this electron cloud, we have these 8 electrons, but the outermost electrons would be the ones that are going to do the bonding. And then we bring in these hydrogens. You know, it also has this electron cloud of its own, and the interaction between those two electron clouds is what causes bonding. Not just a straight line between the O and the H, which sort of simplifies it, but, you know, the interaction of these electron clouds. So, you know, oxygen is going to distort hydrogen's electron cloud, hydrogen is going to distort oxygen's electron cloud, and there's an interaction here that causes these two to stick together. Well, one of the big parts of this is this idea of electronegativity. So electronegativity. Now the definition of that is, simplified definition of that is an atom attracts the electrons in a bond to itself. So it's the force of attraction an atom has for the electrons in a bond. The force of attraction an atom has for the electrons in a bond. So in other words, oxygen is pulling on these electrons from hydrogen. So it's pulling on that electron cloud towards itself. That amount of pull is called the electronegativity. Well, that means hydrogen would be doing the opposite. Hydrogen is, pulling in that direction on the electrons of oxygen. And so there's this tug of war happening between this electron density here, between oxygen and hydrogen. Well, the nice part is we have values for this. Electronegativity can be given numbers. And oxygen has an electronegativity of 3.5. Now, it's relative compared to hydrogen, which has an electronegativity of 2.1. So that means oxygen is pulling harder on the electrons than hydrogen is. And what that does is cause a distortion of the electron cloud with more negatives being pulled towards oxygen, which makes hydrogen a little bit negative deficient, if you want, or a little bit positive, and it causes what is called a polar bond. And then we're going to learn about how shape affects overall polar molecules, so whether they can be a polar molecule or not. All right, so let me move on here. It's sort of the background. So here's our tug of war. We have our two dogs pulling on our frisbee, one pulling in that direction, the other one pulling in that direction, and which one's going to win? Well, you could look at it the same way with this bond. Oxygen's pulling in that direction. Hydrogen's pulling in that direction. We already said this pulls with 2.1. This pulls with 3.5. So, that electron density that's here gets distorted towards the one that pulls harder. There's the word, electronegativity. So once again, it is the attraction an atom has for the electrons in a bond. Now, this is the definition that you've learned, young. You learn this elementary school, middle school, maybe even in ninth grade and high school. Ionic bonds, electrons are transferred. In covalent bonds, electrons are shared. And that's a nice, easy way to talk about it when you're young and your brains are small and you're not quite as smart as you are now. So we have to get a little more complicated than that, because all we're talking about in either bond is a difference in electronegativity. So a difference in electronegativity. So one atom's pulling, the other atom's pulling. Which one pulls harder? Well, in covalent bonds, they tend to have similar electronegativities, which means you're going to have a small difference. So a small difference in electronegativity. In ionic bonds, you're going to have a larger difference in electronegativity. So are covalent ionic bonds that different in that you can give them two distinct definitions like you did when you were young? Well, not really. What it has to do with is which one is pulling on the electrons harder in the bond. Which one has a higher electronegativity, and then a difference between the two atoms' electronegativity. The example I gave you was oxygen and hydrogen. We said oxygen is 3.5. We said hydrogen is 2.1. If you do a difference of those, it's a difference in electronegativity of 1.4. So what does that mean? I don't know. Well, what that means is if we put a cutoff value on this, and the cutoff value depends on the chemistry book, but most often it's about 1.67. If you have a difference in electronegativity of 1.67 or greater, we're going to call that ionic. So this would be greater than 1.67. So that means if you have a bond with a difference less than 1.67, you could call it covalent. Now that sort of muddies the water with these two definitions. And this sort of helps. It is called bond character. So bond character, and you can look up charts of that. They have differences in electronegativity listed next to percentages of ionic or percentages of covalent. So there's that 1.67 value again. And we're talking again there the difference in electronegativity. So that means if you subtracted two electronegativities and you got 1.67, that means it's 50% covalent and 50% ionic. How about that? You can't classify it as one or the other. So what we do then is, instead of saying this one's ionic and this one's covalent, we give it a primarily ionic definition or a primarily covalent, and that's what we did on the very first slide when we said something was ionic or covalent. What we're really talking about there is the fact that it is primarily ionic or primarily covalent. But it would have some percentages covalent and some percent ionic. Greater than 50, then we're calling it ionic. Greater than 50% covalent, we're calling it covalent. And so the idea here is if you could look up the electronegativity values, you could subtract them. You can get a difference in electronegativity, and then you can classify it as, primarily ionic or primarily covalent based on this halfway point, 1.67. All right, still a bit confusing. I think it'll help as we keep going on here. All right, so there is one bond, though, that is a 100% covalent bond. How? Well, because when you subtract its electronegativity, so the difference in electronegativity is 0. There's no difference. And diatomic molecules would classify as that. If you have an oxygen bonded to another oxygen, pulls with 3.5, pulls with 3.5. So they're, the tug of war here is nobody's winning. So nobody's pulling the electrons closer to themselves. And so that is a perfectly shared electron cloud or interaction, and we call that a 100% covalent. It has no ionic character. Why? Well, because they're pulling equally. But they're the only bonds. So the only bonds that are going to have that are ones that have a 0 difference in electronegativity. For our purposes, though, if we were going back to that very first slide, and we don't have electronegativity numbers to subtract, we're still going to go with what we were talking about before. Metals and nonmetals or polyatomic ions. Covalents would be 2 or more nonmetals. The electronegativity trend on the periodic table is, we just got finished with our chapter on periodic trends. Here's another one. Electronegativities will increase as you go from left to right across the table. So they increase going in that direction. And then they decrease going in that direction. So the larger electronegative elements are in the upper right corner, with fluorine being way up there. And then down in the bottom, the francium, that metal on the bottom of the first column, would be the low electronegativities, meaning fluorine is going to attract the electrons very strongly in a bond, whereas francium's not. Group 18 elements do not have an electronegativity. If you look at an electronegativity chart, they're either going to be 0 or they're usually just dashes like this, not showing any numbers. Why? Well, because they tend to not form bonds. So if you don't have any bonds, you're not going to attract the electrons in a bond. Now, what we talk about in class is xenon and radon and a few of the others, under unusual conditions, will bond with a halogen or an oxygen. But for the most part, we consider those noble gases, meaning they don't react. But they are going to come up when we do our dot diagrams. All right, so there's the trend. Again, just another picture. So it increases that way. Some books like to do that instead of increase, decrease. I like to do them all the same. The trend going that way and the trend going that way every time instead of, changing them. Your choice. This is just a 3-dimensional depiction of it. A lab we used to do with straws, where you can see that fluorine is really tall, francium is really small, and there's a definite increase going across this, going from left to right, and a definite decrease going down the columns. All right. Do we understand this? All right, so which of the following bonds is the most ionic? Now, they're all considered primarily ionic bonds because they're metals and nonmetals. You can see I have lithium in the first column, and going right down the first column, lithium, sodium, potassium, rubidium, cesium. They are all bonded to oxygen. Now, according to the trend, and we could start with lithium and oxygen, lithium is in the same row as oxygen. And lithium is over here, oxygen's way over here. So going in that direction, oxygen is definitely going to have a higher electronegativity than lithium, because the trend is it increases going to the right. And then we're comparing going down this column, lithium, sodium, potassium, et cetera, et cetera. And lithium is going to be larger than each of those. So lithium is going to be larger than sodium. Sodium's larger than potassium, et cetera, et cetera. So the question is, which one is the most ionic? So they're all ionic, but according to that bond character, they're more or less ionic.
Bucks basketball team, please report to room 124 at this time. Lady Bucks basketball team, room 124.
All right, so what we're talking about here is a difference in electronegativity. And the greater the difference, the more ionic. All right, well, if that's the case, oxygen is higher than each of the elements it's bonded to here. Lithium is going to be higher than cesium is, according to the trend. So the most ionic is going to be the one with the greatest difference, which is going to end up being cesium. The least ionic of these would be the lithium oxide. So then the second question, which one is the most covalent? It's the opposite of this. It's still the difference in electronegativity, but it is the least difference in electronegativity, which is going to be lithium and oxygen. Again, because oxygen is higher than lithium, and lithium is higher than cesium. So the closest electronegativity is going to be between those two. All right. These pictures represent three things. The top one is a non-polar covalent bond. That's the definition of it. But what we've talked about it so far is that it is a 100% covalent, where there's a perfect sharing. For example, this could be nitrogen and nitrogen. Each nitrogen pulling in opposite directions. You end up with a nice uniform sharing of the electrons because they're pulling with the same amount of force. And it is called a non-polar covalent. The next one, you could see this one starts to pull harder. Maybe this is oxygen and hydrogen, for example. Oxygen with its 3.5 and hydrogen with its 2.1. So you can see that distortion starts to happen here of the electron cloud, where it's not uniform anymore, but it starts to get a little bit of a negative over here. And that symbol right there is the lowercase delta, Greek letter delta. So we say it's a partial charge. That's what that stands for, a partial negative. And this gets, since it's now electron deficient, it gets a partial positive charge, delta positive. And then the last one here, this one is pulling so hard that it actually appears to have, removed the electron. And then that would be an ionic bond. So we have an ionic bond at one end. We have a non-polar covalent at the other end. In the middle here is we call it a polar covalent bond. So that pole idea that it has positive and negative poles would be right in the middle. So that definition you learned, electrons are shared, that's a covalent. Electrons are transferred, that's ionic. It's all really relative. It's really relative because this polar covalent bond has some ionic character in that it has positives and negative charges. And even down here, this negative and positive would have some covalent character in that they are still sharing the electrons a bit. And so that's the chemistry version of bonding. And little more complicated. So what we have to do in my class is you have to be able to look at these substances on this side and be able to match them up to the pictures based on what we just learned. And CNO, carbon and oxygen, they are in the same row of the periodic table, carbon and then oxygen. Remember, the trend is it increases going that way. So this one is definitely a polar covalent, and the oxygen would get the negative charge because it has a higher electronegativity. N2, that's going to be that nice sharing. LiCl, metal and nonmetal. So we're going to call that an ionic primarily. MgO, again, a metal and a nonmetal. SiS, I just kind of made it up because I was trying to make two bonds, or two elements in the bond. Si and S would both be nonmetals, so we'd say that would be that one. And then sulfur would be higher in electronegativity than silicon because it's further to the right. So Si would be the positive, S would be the negative one. I2, again, a diatomic, and SO, once again, a polar covalent, two nonmetals, and O being more electronegative than S. They're in the same column. Sulfur's lower.
Upon this interruption, Mr. O'Malley's 6-period study.
Just a definition here. The electrostatic force is the difference in positive and negative ions. That's what holds an ionic bond together.
Please report to room 120.
These are the characteristics.
Mr. O'Malley's 6-period study. Please report to room 120. Also, the following students stopped by the office this evening: Josh Beltran, Delia Carr, Caitlin Cartwright, Stephen Connors, Kim Dempsey.
They tend to be crystalline solids at room temperature.
Fedor, Robert Gentile.
They tend to have high melting points. It has to do with their strength of their bonds. The strong bond that causes a higher melting point.
Kirsten Rosen.
They are usually soluble in water.
Thank you.
And they will conduct electricity in water in the solution, or if you melt them. So in the solid form, ionic bonds won't conduct electricity. But if you melt them, so form a liquid out of them, then their ions can become mobile and they can conduct electricity. They tend to be crystalline. So this is a picture of NaCl, 10 times its magnification of compared to our eyes. And if you crush this up and then went to, 100 times, it would still have this crystalline shape to it. That was my idea behind that. Covalent bonds tend to have low melting points. In fact, at room temperature, many of them are liquids or gases. They don't conduct electricity. So the definition of something that does not conduct electricity is an insulator. They tend to be brittle, not crystalline and hard. And there's that molecule is just a definition. If you have two or more covalently bonded atoms, we do call it a molecule, and we know that one. All right, so here we have in a covalent bond, and this is going to lead us into our discussion of dot diagrams. You have bond axes, which is the distance between the atoms, the bond angle, which is obviously the angle between the atoms, and then the bond length. The distance between is the length. The axis is just the straight line between the atoms. So you measure the axes length and you measure the angle between the axes. And then down here we have water. And water is known as the Mickey Mouse molecule. And if you could picture this 109.5 degree bond angle, hydrogen, hydrogen, and an oxygen. And that's where it gets that name. So kind of interesting. And then in my class, we did the molecule dance. I learned this one year at my geek convention in Hershey, PA, where a chemistry teacher had us do it, and I thought it was fun. It gets to see who's brave in front of their friends and who's not. But these bond angles, this bond axes idea of the length of it and the angle of it are averages, because these molecules are never just in one place. They're constantly undergoing a variety of motions. And those motions they're going to be stretching, bending, and rotating. And so what we do in my class is you stand up, you put your arms out. These represent your hydrogen molecules, the oxygen represented by your head. And stretching would be you stretch your arms out and bring them back in. And you can do it symmetrically, meaning same time, or asymmetrically, one at a time, or opposites. So there's the first part of the molecule dance. The next is you can bend in that direction back and forth. And so waving your arms in and out. And so again, it creates that angle of 104.5 as an average because it's getting larger and smaller than that. And then rotating would be, now we can't do that very well because we can't spin our hands very well, would be the constant rotation of the atoms. And so we have bending, stretching, rotating all occurring at the same time. And you come up with a molecule dance. And so I like to show them that. There's our picture of the molecule dance. So when I go to basketball games and I see the cheerleaders doing their thing, you can see they are really just doing chemistry.